using these three adaptive algorithms. There are 4 parts in my presentation. Firstly, background. In real-life network, antennas receive and send the signals. The left pictures show an example. Now, the most antennas are smart antennas. Smart antennas is antennas with a smart processing algorithm, and it has 4 main functions. Among the beforemin is the most important one. Then, beforemin. The pictures show the structure of the beforemin. In multiple out antennas, there are many receivers that receive the signals from all of the directions every time. But some signals are useless, even inference the signal we want. So we need to pick and combine some signals. Beforemin can do this work. Beforemin can pick and direct the main beams to require directions. Look at this picture. Several beams enter the receive, but only one get out. Also, beforemin is able to non the interfering the signal. Therefore, we can get a stable and pair beams to the required direction. Our system is based on adapted beforemin. Adaptive beforemin is a beforemin that uses adaptive algorithm. The adaptive algorithm can improve the performance of the beforemin. For example, it can reduce the noise. With the adaptive algorithm, beforemin can change the angle of the required signals over time. In this picture, we studied 3 adaptive algorithms. Signal get into the models and it will be given the vector. These signals combine get the Gn, and here we can get the difference between the Tn and Gn. Tn is a reference signal. Tn the reference signal is stored in the system memory. It's the accepted the signal we want. The difference between the two is the error. Adaptive algorithm will use this error to refresh the weight. First, listen mean sequence the algorithm. This project shows the process of the list of the algorithm. The received data X here is the input signal get into the variable field and get a weight. The weight multiple the received data is the output. You can see that. And at the same time, output is sent to here, and we can get the error. Error is the difference between the output and the reference signal. Then update algorithm use error to reference the weight of the next time. Carefully, it's next time n plus 1, not n. Secondly, data reusing listen mean sequence is an improved algorithm of the LMS. It has the same structure as the LMS, but as we can see, when updating the weight, it needs improve input signal, and current weight doesn't determine the next weight, but will will determine the weight at this time. Thirdly, decision feedback inequality bases the least mean secret. The picture shows the structure of the decision feedback inequality. One feed-forward transversal filter, one sample detector, one feedback filter. These two filters are designed based on least mean secret. Therefore, they can update the width of the signal. At the firstly, the improved data get into feed-forward field. The feed-forward field can remove the samples interference from the received signal and leave some marks in the signal. Then they get into the detector and get the weight and out from the detector. At the same time, output is sent to the feedback field. Feedback remote the inference again and repeat the process. Like they will they will refresh the weight of the next time. Now let's talk about simulation. Our code is from the GitHub. The simulation, uh, the first simulation, mean square error of these two algorithms. When the mean square error is large, the performance of the algorithm is worse. From the picture, we see them as the number interaction increase. The calculated result is close to the expected result. When the number of the interactions is less than 3, the difference between the two is not large, but as the number increases, the gap between the two begins to increase, and even reaching the peak values of about 0.1 at 5 and 6 times. That means that means the DFELLMS performance better than LMF. Secondly, I compare the polar plate of the two algorithms. The exact angle is 13 degrees, and the interference signals is come from the 0 and 13 degrees. And we can see the both algorithms are very good at non-interface signal at S10 and 60, as it is blocked. Um, and 30 and 50s, we need got the maximum power signal. You can is large than this one. The signal. That means the algorithm can direct the mean bits to require directions and non the interference wheel. Actually, the improved algorithm is better than the old one. You can see the blue lines is away from the red one. Thirdly, we compare the performance of the three algorithms at being patent. Uh, from the picture, all three have reached these peaks near our exact angles of 30, which means the threes can send the membranes to the required angles, required directions. Difference is that LMS is slightly slower than the improved algorithm. In other angle, you can this, including the interfacing angle. The MG realized by DRLMS and DFELMS is higher than that LMS. Oh, the negative is just the direction, not not really negative. Which means the anti-interference abilities of the improved algorithm is is better than that of the LMS. Okay, that's my project. As conclusion, the pictures compare the performance of these three adapted algorithms. The simulations results show that DFE-LMS has a similar mean square error than LMS, but these advantages will gradually decrease as the U increase. DFE, LMS, and DRMS are better than LMS in directing the membrane to require direction, and this they have better anti-interferencing abilities. And thank you for listening. Okay.